Can you all hear me?
Yeah.
Okay. On Canvas, Jacob. Go look for it right now. I bet you'll find it. To be module for weeks, I think week number 9 or something. All right, so I want to talk about our next lab. The procedure is actually I think it's pretty easy for the lab. It's the analysis that becomes a little bit of a pain. Okay. Yeah, you're right, Jacob. I put it, the lab wasn't published 5 minutes ago. So sorry about that. So yeah, all the labs now are published. So you can look at all the labs now. I just forgot to publish them a long time ago. So anyway, we're going to look at a lab. The circuit we've covered already. We've covered the circuit in class. It was the Wheatstone bridge and its variants. So I went through that circuit in detail. And so if you forget, you have a video for which you can watch me solve that problem. Okay. So the goal, there's several goals of this lab. Number one is to learn how to build and analyze series, parallel DC circuits. And number two, to investigate Kirchhoff's voltage law and Kirchhoff's current law. And probably this is a fairly straightforward circuit for us to analyze, to cover both items. Okay, so the circuit looks like this, and so I'm going to erase this so I can write on the board, and then I'm going to spend some time discussing the lab. It'll probably take me half an hour, and then the rest of the time I can answer questions you may have before the exam. Okay. All right. So this is the purpose of this lab. Let me erase this now. Let me draw the circuit we're going to investigate. So there's two parts to the lab, and the circuit is essentially the same thing except for one change in part 2. So we're going to have a 6-volt power supply. So you're going to use that same power supply you use for the Ohm's Law lab. And then you're going to have four resistors. And let me label. This point is A, and this point is C. This is R1. This is R3. This is R2. And this is R4. Now, when I design these labs, what I do every semester is I change the parameters. So you absolutely have to use the resistor values that I provide here. Okay? So in the lab, hold on a second. I tell you said R1 equals 100, R2 equals 200, R3 equals 1,000, and R4 equals 470. You have to use those in that configuration. Okay? I purposely chose those to make this lab different from the one last semester. So you lose points if you don't do that. So R1 is 100 ohms. R2, 200 ohms. R3 is 1,000 ohms. And R4, 470. So you want to build this. This is the circuit you're going to want to build. And in part one, we're basically going to be analyzing the following. We're going to look at the current that comes from the power supply. We call it I sub S. And we're going to see how it splits up into these two. So this current plus this current has to be equal to this current. Then that's going to return back to the opposite side of the power supply so that this current and this current has to be equal to that current. And so that's what we're going to be looking at in the first part of the lab. We're going to be verifying that the sum of these two currents equals that. That's the current rule. Okay? Here's a node. There's another node. And we're going to be analyzing the currents going into the node. So what are you going to do? Well, first of all, you're going to measure the power supply voltage. Okay? So you want to measure that. You do, and before you build the circuit, you want to measure R1, R2, R3, and R4. And of course, there's uncertainties associated with them. I'll talk about that at the end. Okay, so hold off your questions on the uncertainties in these values. So once you measure these, then you're going to measure I sub S. How do you do that? Well, you're going to have to put the multimeter here and measure I sub S. Use the big multimeter. Why? Because it's more accurate. Now, here's the thing. I'm going to let you choose. I'm going to let you choose whether or not you keep this multimeter there the rest of the way in part one. But let me tell you about some advantages and disadvantages about keeping this or removing this. If you keep this in here the rest of the time while you're measuring voltages, just be aware that, if you do something strange, you can blow a fuse. Okay? So if you keep that in, you're going to be measuring delta V R1, delta V R2, delta V R3, delta V R4. I'm not going to have you measure the current through this guy, the current through this guy, the current through, because it's a pain. It's a pain to do that on this board, because your circuit's going to be on this board. All right, this is the I'll show you the circuit close up later. Okay, so it's up to you whether you want to leave this in there or not as you're doing this measurements. If you leave them in, just realize that if something goes wrong, you can blow a fuse. Okay. Now, if you take that out, that causes a different problem. If you put this in, measure IS, take this out, and then make these measurements, that's going to have an effect. Why?
Because it's going to be a different current going through the system, whether or not the ammeter's there.
Yeah, why is the current different?
Because the resistance of the ammeter is different than the resistance of the wires.
That's right. The resistance of this is not going to be zero. So that leaves another question. What current setting should I put that at?
You're going to have to calculate the equivalent resistance of the system and then use Ohm's law.
Yeah, to do that. I guess the question is, I mean, there's several settings you can use to measure the current. Do you want to use a lower current setting or a higher current setting? And that's a problem. Go ahead.
I don't, I was gonna say I don't know actually. Like maybe you want to start high and then go lower based on the reading you get.
Yeah, you can do that. Here's the thing though. If you go to a lower current setting, you do get more sig figs. But guess what? You have a higher resistance. Okay. Also, you're going to have to read the manual. If you look at the manual, the accuracy is different on different scales. Okay? Your accuracy changes on the different scales too. So the problem you're going to have is, okay, well, if I set this to a higher current setting, I'm going to get less sig figs, but my resistance is lower. If I set this to a lower, I'll have less sig figs on the high current setting. If I set this to a lower current setting, I'll have more sig figs, but a higher resistance. So my systematic error is higher. This is something for you to consider.
Would it be smart to measure the voltage of the power supply after putting the ammeter in the circuit?
For this power supply, because this power supply is not well regulated, so I don't know if the ammeter would make a big difference.
Okay.
Right? I mean, I think what would make a big difference is these values.
Right, yeah.
Because if you're drawing more current, that's going to affect this thing a lot more.
Yeah, I was more talking about for like consistency's sake than like the actual effect of the ammeter.
Oh yeah, but it's really not going to affect. It's going to affect these values.
Gotcha.
Okay. Okay. So now that we've measured this, now we've measured everything we can measure, and so now you can calculate. And I'm writing I1 instead of IR1 because I'm too lazy to write all the subscripts. You got to calculate all that. How are you going to calculate this? Air propagation. I'm sorry?
I was just answering the question.
Okay. No, I just didn't hear. I'm sorry, I just didn't hear what you said. So you will be using air propagation to calculate these. This is easy because it's just a division, right? So the air propagation for dividing is easy. Of course, you're going to need to know these uncertainties. And again, I'll tell you how to get the uncertainties. You're going to have to use the manual. The manual tells you what the uncertainties are. So you actually have to read the manual. Okay, so. Okay, then you're going to calculate you take I1 yes. You're going to take this plus this. In other words, this plus this has to be equal to that. Okay, so this is where you're verifying KCL. And of course, you got to calculate the uncertainties, right? You got to calculate the uncertainties too. So you need delta I sub s too. How do you know whether or not two values agree?
The uncertainty overlaps.
Yeah, the values. Remember, every time you make a measurement, you're not measuring a number, you are measuring a range of values. And so you want to make sure that the range of both ranges overlap each other. If they do, then you have agreement. If you have a range of values here and a range of value here, they don't overlap, then they don't agree. There's some sort of systematic error you're dealing with. Okay? Because I asked you that question many times in this lab. Okay, so that's part one. Okay, but then there's some questions too. And one of the questions asks you to verify KVL. Basically, all you got to do is pick a loop, whatever loop makes you happy, and sum the voltage drops around that loop. And calculate the uncertainty in that sum. Because you want to see if your sum, plus or minus the uncertainty, overlaps 0. That way you can say whether or not your experiment agrees with Kirchhoff's voltage law. So you got to show your work on your calculations. Okay, so let me say something about showing work. You got to calculate 4 uncertainties here for I1, I2, I3. Isn't the process for calculating these uncertainties the same?
Yeah.
So I don't need to see all 4 of them. I just need to see one of them for each table. Okay?
Right.
So for each uncertainty calculation, for each table, just show me, so just show me this one for table 1. For table 2, show it again, but you're going to have different values. Okay? Because otherwise you're going to end up doing this 12 times. There's 3 tables. But then again, for this one, when you calculate the uncertainty, just show me one of the 2 for each table. Does that make sense?
Yeah.
Because otherwise your lab is going to be many pages long. Because you can see, you have 12 of these to do, you're going to have 4 of these to do. Now granted, each one these are not long, I mean, this is easy to do. The uncertainty in this thing is easy to do. Okay. So how do you get I sub s, the uncertainty in I sub s? Well, you get it from the manual. Okay. So that's part 1. Any questions on part 1? It's not anything not clear in part 1. All right, so part 2, what you're going to do is same circuit, but this time you're going to make this permanent. So in part 2 now, you will make this measurement, this measurement, this measurement. You're going to make all these measurements, not this calculation. We're going to make all these measurements and all these calculations, except for this last one. But you're going to have this in there, and so you're going to measure I'll put it here. You're also going to measure this. Now, this has to be there during the entire process. This one can't. You know why? Do you know why you can't have this one in there the whole time in part 2? Anybody want to guess?
Because they're going to need to use...
I'm sorry, say that again.
Aren't you gonna need to use it to measure the other voltage
Yeah,
drop?
you don't have enough multimeters, right?
Yeah.
You would need a third one to go and measure voltage, 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 voltage. Okay, so you have to take that out. You have to measure isobest and then take that out. This has to be there the whole time. And the reason why this has to be there because this actually completely changes your measurements. Right, that does not. But this changes because now you've shorted these 2 points. Now, you're going to do part 2, you're going to do twice. In fact, in part 2, you're going to be doing these measurements twice. In one case, and this is going to be the small multimeter, by the way. You're going to do it once with current setting the highest current setting that yields measurable value. I don't know if you can use a 10 amp scale. Okay. So you're either going to be using the 10 amp scale or the 200 milliamp scale for this. Why do I want you to do that? Why do I want you to use the highest current setting possible?
Because it'll have the least resistance.
Yeah, because it has the least resistance. It'll have the least effect on your circuit. And then you're going to do it again with the lowest current setting. And I'm running out of space. That doesn't blow the fuse. Why am I having you do that?
For more sig figs?
Yeah, I mean, that's true, you'll get more sig figs, but what else? Why else would I want you to look at the lowest current setting?
The change of resistance due to the change of setting?
Yeah, I want you to see the effect the resistance has on your circuit. I want you to see what happens when this changes. It's not going to be a huge difference, but you'll see it. Okay? And so you're going to then calculate the following. See, what's going to happen is when you put this meter there, some current will go this way. And so IAC is going to be this minus that. Oops. See, without the meter there, these two are equal. When you put the meter there, they're not, because you're giving the electrons another path. So we're going to measure that. You're also going to calculate because this current plus this current gives you that current. So again, we're verifying the current law. Does this difference agree with your measured value? Does this difference agree with what you measured? That's what we're looking at. Okay, so we're verifying the current law. And then there's a bunch of questions at the end. There's more questions at the end of part 2. So the measurements are easy, right? Because you're going to put a multimeter here, 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 and here to measure the voltages. The currents are easy. So the measurements are actually pretty easy. Okay. The hard part of this lab is all the calculations you got to do. There's no graphs, by the way. But you got to do a ton of calculations. There's a ton of air propagation. This is probably the most intense lab in terms of air propagation you're going to do this semester, I think. There's going to be 2 more labs you do this semester where you do air propagation. But I don't think they're as intense as this one. Okay? So after the exam, if you get a chance, just wire the circuit up and make the measurements. Because it's really not a hard lab in terms of the procedure. It's a hard lab in terms of the analysis. All the air propagation you're going to be doing. Okay? Questions on this? Let me show you the circuit then. Okay, I'm going to unplug my microphone and I'll forget.
And this is due the Monday we come back from spring break.
I'm going to make it to the Tuesday so you can ask questions. But
Okay.
if you wait until Monday to do the lab, you'll never get it done.
Yeah, no, I was just wondering.
Okay. No, but I'm just telling people in general because
Okay.
what happened over the weekend, people tried to do Ohm's law lab at the last minute and they were struggling. I'm not going to always be available like on the weekend to answer questions, and so that's why the earlier you get started, the better. Because otherwise, you're going to struggle through it. Yeah.
Professor,
Yeah.
does Tyler have a video for this one?
No, because this is I think it's a straightforward lab, so I didn't have him make a video for this one.
Okay.
And if you think it's not at least in terms of the measurements, let me know. And I need to connect my camera. And you're going to see the circuit built anyway, so you can actually go to this video and just look at the circuit. And there's multiple ways to build a circuit. So here is the circuit. Here's my power supply. R1, R3, R2, and R4. Okay. So I'm leaving this here so if you have trouble, you can just use this picture to build your circuit. I could have, if I wanted to, just connected these two together. I did make mine a little bit more complicated. You see the orange wire and the white wire? What do you think they're for?
The ammeter.
Yeah, that's for the ammeter for part 2, right?
Yeah.
Yeah, so I can use that for the ammeter for part 2. And also, if I can connect the ammeter between this point and this point to measure I sub S. So I can pull this one out and I can pull this one out and connect these to the ammeter to measure I sub S. I set it up so it's easy to make those connections. That's why I set it up this way. Like I said, instead of putting this yellow wire, I could tie these two together in one of the holes. The same thing up at top. Okay. So yeah, I'm purposely putting this here so that if you have trouble wiring it, you have something to go with. You don't have to wire it this way. Normally I would probably wire it a little bit differently, but I just did it this way just to show you as an example. Okay. And for me, I tape this thing to the board because that way it doesn't move around. The first time I did this, it was very annoying to use this thing, and so I just taped it down. It made life a lot easier for me. Any questions about the circuit?
Would you need the orange and white wire there for part 1?
No.
We could just put that it?
Yeah, you can pull that out.
Cool.
Yeah. I have that, I have that there just so to show you how you can measure the current for part 2. So really for part 1, it should look like this. Okay. And then for part 2, you put those two wires there. At least this way you have a reference. So this is kind of why you don't need the video from Tyler, because really this is it. All you're going to be doing is putting a multimeter here, 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 and here to measure voltages, right? Because you're always putting it in parallel. So here, here, over here, and over here to measure the voltages. It's a little blurry, sorry.
On your particular circuit, where did you measure voltage? Just at the
You mean the voltage across the resistors?
power supply.
Oh, I can take these out. Right, I can pull these wires out and connect them directly to the multimeter, or I can do this. Hold on a second. You see where I inserted those two wires? I can connect these to the multimeter.
Okay, awesome.
Okay, either way is fine. I mean, there's a lot of ways to do this. So this is just one of them. Okay. Are there questions? Oh, I was going to, I kind of, on Tuesday I went through this kind of quickly. But, this is a tool you're going to be using later on this semester. It measures voltage on the vertical axis and time on the horizontal axis, so you can actually look at signals that is a function of time. So this is called the oscilloscope. And 2 weeks after spring break, we're going to be doing this lab. Now, yours is, I think I said this on Tuesday, you don't have this is a nice one, I mean, compared to the other one. This is my own that I bought myself. This has 2 inputs. And to go from one input to input, the price of this goes from $20 to $80. And so we couldn't add this to your kit. But this is really what you should be using. You're going to be using one with one input, which is really not that useful, but at least you'll learn how to use a scope. Okay. But you're going to have a lab where you're going to demonstrate that you know how to use this. Okay. And I'll try to give you some resources on how the scope works. The only problem is there aren't any resources that show you how this particular one works. But the resources that there are online show you how the large ones work, the ones you actually use in real life in the lab. Okay, so I'll show you that, but at least to give you an idea of what they're useful for. They're measuring signals as a function of time. These are more powerful than the multimeter. Okay, questions on the lab so far? So I need to say one more thing. Oops, 1 second. Okay, before I forget, I'm going to unplug that camera and plug in the microphone so you can hear me okay. Okay, we need to talk about uncertainties. And one of the things that I like about this lab is, you do get the manual, and engineers have to learn how to read manuals, okay? And that's a tough thing to do because engineers usually don't write manuals very well. These are not very well-written manuals, unfortunately. Some of the terminology in here is very strange. But reading the tables is easy. So how are we going to determine the uncertainty in a voltage measurement? How are we going to determine the uncertainty in the current measurement? So let's say we measured something with the meter. How do we determine the uncertainty? So let's say I measured the resistance, and I got this value. So multimeter value, okay? How do I know what the uncertainty is. Well, I have to take out the manual. Now, what's nice about this manual, it doesn't tell you the uncertainty based on just random errors. It gives you the uncertainty based on random and systematic errors. We call that the accuracy. But the way it's written is very difficult to understand. So I'm gonna make up something. Let's say, just for the sake of making the calculation easy, let's say the manual says the accuracy is this. What the heck does that mean? This refers to the least significant figure. So it says the least significant figure is off by 5 digits. So this could be either 250.6 or 249.6. So this is the error on the least significant figure. But then there's also a percent error. Let's calculate the percent error. One percent is 0.01. Okay. And so this is the least significant figure. So you have an error of 2.5 ohms plus this. So it's really 3 ohms. This 0.5 digits is the error in the least significant figure, which in this case is 0.5 ohms. Take this value plus this value, and you have delta R is 3 ohms. You always keep one digit in uncertainty. So then delta R is 3 ohms. So we would say that R is 2.50 plus or minus 0.03 times 10 to the second ohms. Right, okay. Questions on that? No questions? So is this okay then? Same thing whether we're doing resistance, voltage, or a direct current measurement. This is how you're going to get the uncertainty value. So in your table, where it says R plus or minus delta R, of course, this is going to come from air propagation. This comes from air propagation, but this one does not. This one comes from your measurement. Again, you're going to use these. You're going to make use of these, okay? One of the things, like I said, one of the things I like about this lab is that it forces you to read manuals, because people generally don't like to read manuals. And when you take a class with Pattingale, he's going to tell you about how important it is to learn how to read the manual. Okay, because I know some of you guys are going to take engineering courses, or you're probably taking them now. Questions? on this lab at all. So I'm going to make this due on the 6th. I know I'll change that. But please get started right away. Okay. Now, the other thing too is, based on the last lab, I kind of get the idea that people weren't looking at, either they didn't watch the entire video on the Ohm's Law lab, or they watched part of it, or I'm not sure. But if you ask me a question and the answer is in the video, then I'm going to say, watch the video. I'm going to refer you to the video. Okay? Because otherwise I'm going to be spending tons of time answering emails because people didn't watch the video or omitted part of the video. Okay? So I just want to make sure you go through and watch the video. So if you ask me a question, the answer is on this video, I'm going to say, watch the video. Okay? So questions about, if you don't have questions on this, do you have questions? We have a test later on, so you have questions before the test.
Can you walk through number 15 from the homework?
Number 15, let's see. Okay, so I'm going to erase all this then. We have two resistors in parallel. And two capacitors in parallel. And we have a switch. So R1, R2, C1, C2. By the way, since these are in parallel, can I just replace them? Okay, is that okay? So the question asks for the charge Q1 and Q2. Now, this is, you're all okay with this, right? No objections to this?
Yeah,
I just use a parallel rule. When two resistors are in parallel, the resistance is a product over the sum. For three, that's not the case. But okay. So what's the equation for the Q, the RC circuit? It's going to be Q max 1 minus e to the minus t over RC, right? And then the voltage across the capacitor is going to be what? Delta V of the battery, 1 minus e to the minus t over RC. Right? So these two capacitors have the same voltage as this one, isn't that true? They're in parallel, yes. Right? Okay. So if I can write the equation for this one, what's the battery voltage? Is everyone's the same? They're different. Actually, I think it's this. So isn't it true that the voltage across the capacitor is going to be, oh, this is going to be a pain to write. Let me write it like this. And then since the voltage here is the same as the voltage of these two, then Q1 is going to be C1 delta V. I don't want to rewrite that whole thing. And Q2 is C2 times that. That's it. Now you have a calculator, so you can figure out what these numbers are. Is that okay?
Yeah, I see where I made my mistake.
Okay. Other questions?
Can you go through number 1 on the practice test?
Number 1 on the practice test. What is that one? Oh.
It's the capacitors where you replace the battery with a small capacitor after it's all charged.
Okay, let me... I'm going to open up the file.
Okay. I could read it to you if you'd like to.
Yeah, I actually got it already. Okay, so you have a 24 microfarad capacitor and a 8 microfarad capacitor. They're connected in series to a 60 volt power supply. So let's see. And then I can reduce these into a single one, right?
Yeah, it's 6 microfarads, I think.
And so the total charge then is going to be 60 times 6, right? Right? So then it says, I take this out. So this thing has 360 microcoulombs, and I connect it to a 2 microfarad capacitor, correct?
Yeah.
And so what's going to happen is they're going to share charge until their voltage is the same, correct?
Right.
So the total charge is still going to be this. And it's going to be the charge on each capacitor, right?
Right.
So the voltage is going to be 306. Oh gosh, that's bad. That's a coulombs. So the voltage is going to be 45 volts on each capacitor, correct?
Yeah.
So it means the charge on each one is going to be 45 times 6. I'm sorry?
Right. I was just going to say it's going to be their capacitance times that, which is what you're doing right now.
And then what does it say? Oh, and then each one, because the two are in series, they're both going to have 270 microcoulombs, right?
Right, yeah. If they were in parallel, how would that change? Would it be that would you have to calculate each based on like the Q equals C delta V thing because they have the same voltage across them?
Yeah.
Gotcha.
Okay. So then what happens next? I insert a dielectric into this one, right?
Right.
Okay, so now they're both 6 microfarads, right?
Because the kappa is 3? Yeah.
Yeah. That means that they're going to have the same amount of charge on them.
Right, so each one would have 180 microcoulombs.
Yeah. And so the energy afterwards on this thing is going to be Q squared over 2C. The energy you have here is going to be so basically the numerator went up by a factor of 4, the denominator went up by a factor of 3, so U final is 4/3.
4/3.
U initial. That's it. So it went up.
Yeah, can you that last part that you did, the V final equals 180 microcoulombs squared over 2 over or 2 times 6 microfarads?
This is a U final, so this is the energy stored.
Oh, okay.
So if you remember, U is, this one's hard to remember. All right, that's the energy. That's the equation for the energy stored. You can write it this way or that way. I wrote it this way because it's easy for me to see, easy for me to compare. Because I didn't have to calculate the voltage here. I just know that if they're going to have the same capacitance, they're going to have the same charge. That has to be the case. And so I just use the Q's.
Does anybody else have any questions? Because I have more, but I want to, let other people go.
Nobody else have questions?
I had a question about number 2 in the practice exam.
Number 2, okay.
Sorry, Christopher.
That's all right.
What is your question?
So I was just wondering, I was trying to do it by using Kirchhoff's laws, but then whenever you sent your key, you were saying that you could do it with not a lot of algebra and you were able to solve for it without. And I was just wondering how you did that, like how you would approach this problem.
I use Kirchhoff's laws, though.
You did? Maybe it was just like a bunch of shorthand then.
That's right. So
Okay, I was like, where'd he actually set it up though?
yeah, and you know what? That was I thought I had a key, but I didn't have a formal key, so that was like my scribble when I read a test. And so I was in a hurry to give you guys something. So let me try to draw this. What time is it? Let me try to draw this. This was 10 volts. And then what's the other resistor? That's something blocking.
25.
25, okay.
And then the final battery is 5 volts.
Okay. I drew a bad picture. Okay, so I'm going to use the loop rule, okay? Let me use the loop rule here. What's the voltage drop across this?
Doesn't it have to be 10?
It's 10, right?
Yeah.
Okay, so then I is 10 over 64. So I did use a loop rule. It's very compact.
Oh, like I was setting up matrices. That's ridiculous. Okay.
And that's the thing, you know, if
really
you don't
thinking
have to
about it.
follow the procedure all the time, right? That's why I said there's not a lot of algebra required, because each loop can be solved pretty straightforward. I got to find the other loop. You do have to look at it though. Look at this loop. I need a different color. Let's look at that loop. So you have 5 plus 10 plus 15 minus 25 times I equals 0, right? Isn't that true? And so I is 30 over 25.
You're assuming that the current doesn't change at any point in that loop?
Well, there's no voltage drop here, right? So it doesn't matter.
Well, but isn't when it reaches
This point?
the middle part? Yeah. No. Sorry, to the left a little more. It's going to split to go through the 25 ohm resistor and the 128 ohm resistor, right?
Yeah, that's true. But remember, I'm using the loop rule, right? This is the loop.
Yeah.
So even though the current could change, that doesn't necessarily affect the change of the voltage in that loop.
Yeah.
It should still be equal to 0. Oh my gosh, this is a way easier problem.
Let me see the other one. So now I know this is 1.2 amps. I know that this is, I think it was 0.156. And I can do this loop now, right?
Yeah, no, I see it now.
Okay. So that's what I mean. There's not a lot of math. But see, I was trying to be very conceptual, right?
No, it definitely is. It's just, you were right what you said earlier, where I was just getting in a very procedural way where I set up and I was trying to solve for all the unknowns all at once.
Yeah, and one of the things to, you take a minute and look at the circuit. If you can figure things out quickly, then just do it. And then what'll happen is you'll say, oh, I can figure this out. And then, oh, I can figure that. And if you get to a point where you can't figure something out, then yeah, you got to start writing a bunch of equations down.
Is there any way that we can redraw this circuit in a simpler or like in a different way that makes it kind of look a little cleaner?
That's a good question. I mean, it'd probably be worse if I shrink. This is a wire, whether I make it a wire or I do this. I don't know if this helps you. If that makes it better or worse. Sometimes people don't like triangles. All right, I can do the same thing here. Does that help or not?
I was thinking of maybe combining the resistances Like,
Yeah,
the-
you can't.
but the voltage is, there are 3 different power supplies, so we can't do that.
No.
Could you set up the loop for the rightmost square, the one that you just changed into a triangle?
And Jacob, you're right that we could do each one of the resistors. You want me to do this one?
Yeah, I just wanted to make sure I'm setting it up correctly.
Okay, so I'm gonna go like this. Let's see, I have 5 volts. I don't know what you want to label this now. We're gonna be. I'll write.
I assumed the current was going downwards, so it'd be a positive
Okay.
across that resistor.
This one's 30 volts, right? 25
Yeah.
times 1.2. Is that right? Yeah, I think so.
And then we were just solving for the I-128.
Yeah.
So once we know these, we can find the current going into that node right there between those 2 resistors, right?
You mean here?
No,
this
the top
one.
one. Sorry.
Yeah, you can find
Yeah.
that right away. You'll know
Cool,
this and this,
okay.
so you can figure that one out.
Yeah, I know you didn't ask for it or anything. I'm just trying to make sure I.
Yeah, and the
Like
key, I
understanding.
think, in the key, I think I actually have this value. I think this came out to be 0.195 amps. And this was like, something like that.
Okay, so when you're asking calculate the current through the 3 resistors, you want the 3 currents, or do you want the total current?
Well, you can't do the total current, right? This could be the 3 individual ones. So you want the current through this one, the current through that one, and the current through that one. So you want 3 separate values.
Oh, okay.
Yeah, Jacob, the 10 and the 64 is the easiest one. That's the first thing you want to see. It's like, oh, I can get that. It's not always going to be like, this simple, but it's not simple if your mindset is setting up the equations. You do have to take a minute to look at it and say, you got to ask yourself, what can I figure out first? And Jacob, when you looked at the 10, the 15, and 120 there, yeah, you can do that too. You get the same equation, right? The bottom loop, so if this side's positive, I would say the current's going this way. The current through this resistor is going from left to right. The current through the 5 volt, I'd have to calculate that. I forget what it is because I have to look at all these values and then use the current rule. Then I could tell.
Isn't the current through the 5 volt just going to be the same as the current through the 25 ohm resistor?
Oh yeah, you're right. You're right. So it is that way. Sorry, I didn't see that. Yeah, it's doing this. So it is 1.2 amps going from right to left. Yeah, one ohm you have to use Kirchhoff's laws to figure out. I think was it the 10 amp, the 10 ohm, the 10 volt power supply, if I remember correctly.
Yeah, because you have like 3 currents going into that middle node.
Yeah. Yeah, one of the things I'm trying to get students to do as they learn physics is to obviously know the procedure for solving a problem, but then you should also know when it's okay to avoid it, right? Because that's a lot of work, isn't it?
Right, it's like using the quadratic formula instead of like the, completing the square or something simpler.
Yeah, when I teach 205, I tell people, know when you can and you can't use the equations, when you do kinematics, right? And so, same thing here is you can always use Kirchhoff's laws, that's true. You need to know when it's going to be more painful to use Kirchhoff's laws. Because Kirchhoff's laws will work in every case. It's just that in this problem, if you started setting up Kirchhoff's laws, it would be difficult.
Right.
You would need 3 loops. Of course, the loops aren't that complicated. Right, this loop is easy. So maybe if you wrote this first one, you would know right away, I know 1 current already. So you just want to, I'm just trying to get you guys to think a little bit about, look at the circuit carefully. Is there anything I can figure out right away? You can try to go as far as you can before you can actually start using all the equations.
Mind at least walking through the setup of part 4 or of question 4, the cloud of electrons and the protons and the ammeters.
Okay, somebody, let me do 3 first, and then I'll do 4 because somebody in the box, in the chat box.
Oh, that's right.
Okay, so let me do 3. In 3, looks like an RC circuit problem. Really, it's understanding Kirchhoff's voltage law.
Three is pretty much the same problem as number 16 in the homework. Kinda.
I have to look at number 16. Yeah, in fact, number 16 is like the one I did in class, right? The last problem I did in class. So let me look at number 3. So we have a 45 volt power supply, and then we have a resistor. Yeah, by the way, the software I used to draw these pictures, it didn't draw the regular resistor symbol. So this is 2200 ohms. Capacitor. Then this is 5600 ohms. And this is 470 microfarads. Okay, so I want to know the rate at which this thing is charging up, basically I, when the current through here is 2/3 of its maximum value. So what's the maximum value?
45 volts divided by the total resistance of the circuit.
Yeah, be careful because actually that's the current at t equals infinity. At t equals infinity,
Oh, so
this is an open circuit, right?
right, so it's just the top resistor?
Yeah. Okay, so 2/3 of that actually, let me calculate that. Hold on a second. I get 13.6 milliamps. So then the voltage drop across this one is what? About 30 volts. Let's just say 30 volts. What's the voltage drop across this one then?
Negative 30?
No, this is 45.
Oh, 15. Sorry.
15. So what's the voltage drop across this one? What's the current through this
15.
one? 15 over 5600, right?
Yeah.
Uh, 2.68 milliamps. So you have 13.6 going in, 2.6 going through this one. Where's the rest? Going through the capacitor. It's the rate at which the capacitor is charging. Okay. And yeah, when I gave this problem last semester, people were setting up the differential equation. And I try to do it, so if you look at the key, I try to do it the hard way. It says hard way. It's painful to do it the other way, actually.
So I was looking at the comparison between the hard way and then this way, but I guess my question is, how does this answer the question in terms of the time rate of change?
Because dq dt is I.
Oh, yeah, okay.
Right?
So I could just answer with the I, and
Yeah.
that would be, okay.
Right, but the point is, do you know it? I guess the question is, I'm trying to get the student to understand what is a time rate of change of charge. It's current.
Which is just current. You
Yeah.
were just asking for it. Sneaky, sneaky. Okay.
And then what was the part B? Part B, how much energy is stored in the capacitor? Well, you just take this square times that divided by 2. Right? So number 4. This looks like horrendously complicated and right, this looks horrendously complicated. But again, conceptually, it's understanding the concept here is what's important. This is really a resistivity question, which is very hard to find a good resistivity question. And this is a real life application. Of course, the real life application, I mean, there's technical details that I leave out, but that's okay. So a particle hits here, right? And you collect the current here. You collect the current here. And so let me call this I sub B. Let me call this I sub D. I sub C. I guess I should write like this. And I sub A. Okay, So this whole thing is at the outer edge is at an equal potential. It's a conductor. It's got to be at an equal potential. Electron hits here. What's the potential difference between these 2 points compared to these 2 points?
0.
Why is it 0? So you're saying this point is at 0 volts?
No, I was saying that the difference between.
Oh, okay. Yeah, you're right. So they're equal, right? This potential difference and this potential difference are equal.
Yeah, so their difference is 0.
Okay.
Actually, I don't. I thought I understood, but I don't. Why is the potential difference between those 2 points equal? Between those 4 points, I guess.
Let's say this point is at V. Okay?
Oh, and then the surfaces are both at 0. Okay.
Yeah. So that means delta V is the same. So that means if this resistance is R sub A and this resistance is R sub B, then R sub C and R sub A. That means that R sub C has to be equal to I sub A, R sub A. Isn't that true? Because the delta V, you said the delta V's are the same.
Yeah.
Okay. Now, what's R sub A and what's R sub C?
Is it the resistivity over times the area of the plate?
Yeah, so it travels this distance, right? So if this point is x, the distance that the charge travels from here to here is going to be L over 2 minus y, right? And then R sub A so you put these in here and then solve for y. Of course, you do the same thing for x, so you can you just write down the equation for x.
Right.
That's it. But this is something that's used in real life, that in the lab. The only thing that I'm missing there is, you have to amplify the signals, so all the stuff that complicates the issue I ignored. But that's essentially the principle. You'd be amazed at the ingenuity of engineers. And the basic principle is actually pretty straightforward. And now I'll be honest, this was actually on the test, that was to me the hardest problem on the test, even though mathematically it was easy, conceptually it was a harder one to see that.
Right. I remember when we derived resistance from resistivity, but isn't resistivity in units of like ohms per area?
Resistivity? No, it's ohms per meter. I'm sorry, ohms times meter.
Oh, okay, I see. I was just trying to get the units to cancel out and I couldn't, but I see it now.
Okay.
one last question, if you don't mind. I think it's quick.
Okay.
So it was actually from the multiple choice. If a 2 milliamp beam of electrons is traveling to the left and then 2 milliamp beam to the right, what is the total current of the combined beams?
So current is NQVA, right?
Yes.
Okay, so if you swap the directions of, if you swap the signs of these two, you get the same thing, right?
Okay. I was just making sure because, like, my reasoning of it, I was like, direction should still matter. But for some reason, I was thinking because of the answer, it doesn't.
Yeah, because you're swapping both.
Yeah. Okay. Because it's an equivalent charge and an equivalent. Got it.
Yeah.
No, one's positive and one's negative, right?
Yeah, that's what's. No, but I was thinking that because of the answer, because they were similar numbers, the direction was irrelevant and they just combined, but that shouldn't be true. Direction is relevant.
Yeah.
Right. I was just saying that you said they're equivalent. I was just confused because you said they were equivalent charges, but I mean they're equivalent like magnitude, but they're opposite.
That's what I meant.
Okay. I just want to make sure I wasn't misunderstanding.
Yeah, no, because he picked really nice numbers, it works out to where it's like it just doubles, but it. Yeah.
Yeah, negative charge moving to the left is the same thing as a positive charge moving to the right at, same speed.
Yeah. Yeah. Okay, thank you.
Sure.
Also, I don't know if it helps you for next semester, but you technically now have a video of you going through this exam.
Actually, you're right. I went through every single problem, didn't I?
You went through every problem except for like a couple of the multiple choice.
Okay. I'm going to have to save this then.
Yeah.
Maybe I'll have to, I'll edit this video. That's true. I did all of them. I didn't realize.
I'm actually going to help you get even closer because can you explain 5 for me? I think I understand why the answer is what it is, but I'm not like certain.
Number 5. Oh, the
multiple choice number 5.
Okay. 120 watt bulb. I'm sorry. A 60 watt bulb is rated at 120 volts. So if you look at the stamp on the bulb and it says 60 watts, it's only 60 watts when you put 120 volts across it. Okay?
Gotcha.
And so if they're in parallel, both bulbs are going to get 120 volts.
Right.
So the total wattage is going to be 60 plus 40.
Oh, okay. I was missing that piece of information that 120 or that the 60 watts is at 120 volts. I thought it just meant that was the maximum amount of voltage you could put it across.
No, that's what it's rated at. Right.
Gotcha. Okay.
We can't find. Unfortunately, there's hard to find incandescent bulbs anymore. But now they're all LEDs. They use like 9 watts or whatever. But yeah. So the stamp on the bulb is the wattage when you put 120 volts across it, because that's what's assumed. Because everything in your house is in parallel.
Right.
Yeah. Okay. So that's true.
Thank
I
you,
have
Professor.
even two of the multiple choice questions added too. So yeah, I'm going to have to do that. I'm going to have to use this for the key. That's a great idea. All right, so I'll see you. I have a meeting at 11.
Thank you, Professor.
Sure, no problem.